In this video, we are going to solve a question on reaction rates. Now look at this. The following data we have obtained after an experiment on the rate of the composition of nitrogen oxide was studied at various concentrations. Now look at this. We have number of times of experiments according to this table, and we have the concentration of nitrogen oxide, right? And in this case, if you look at it very well, the name is not actually nitrogen dioxide, right? It is nitrogen pentaoxide because we have 5 oxygen here, but at the same time we have what? The rate of reaction. Now the reaction was actually repeated 3 times with different concentrations. And one thing I want you guys to know is that whether the concentration of a reaction is increased or decreased, the rate constant will always remain the same. That is the reason why it is constant. That is, the rate constant K for this reaction is going to remain what? The same, whether a particular reaction is increased or decreased. So now let's move to the solution to this question. But I would like to actually explain this question in an orderly manner. That is the steps. I'm going to show the steps involved in how to solve any question like this. The first thing you're going to do, which is the first thing that you're supposed to do, is that you're going to actually write out what the rate expression for this experiment. You write the rate expression for this experiment using the rate law. And don't forget that rate law simply states that the concentration of the reactants must be in respect to the order of reaction. Is actually an expression that actually shows the rate of reaction with respect to the concentration of the reactant that are present in that reaction. But in this case, we are talking about we are basically talking about the reaction rates, and what happened is that we are talking about the composition of nitrogen pentaoxide in this case. So that shows that you have to write out the equation to this reaction first, and in that scenario, you're going to have N2O5, which is decomposing in presence of what catalyst? No catalyst. Then you're going to have N2O4 as the product plus, I think, 1/2O2, which these are the products, and this should be in gaseous state, right? While this as well should be in what? In gaseous state, and this as well should be in gaseous state. So everything they all have equal state. That is, they have the same states, and that scenario, say they are what? Homogeneous chemical reaction, because everything occur at the same state. But now let's go. After writing it out, the first thing that you need to note is that we have single reactants in this case. That shows that we'll be working with respect to this single reactant. That is the major thing we're going to be doing. Now the next one that is that write out the rate expression. Now to write the rate expression, you have to take note of this reactant, and in that case we're going to have rate expression equals to what? K, which is the rate constant. It is very, very necessary. Then multiply the concentration of the reactant raised to power of X, and in this case X is basically the order of reaction, right? And K is the rate constant, right? This rate is actually the rate of the reaction. That is the speed at which the reaction occurs. So that's basically what your rate is, and the rate is always provided as well in the reaction. And as you can see, this is the rate of reaction in this column, in this table here. And now look at this column here as well. This is the concentration of this reactant, and the number of experiments, that is the number of times the experiment is repeated. Now we are now asked to determine the complete rate law for the reaction. Now, although this is the rate law, actually this is the rate expression, but there is something that is missing, and what is missing here is the rate constant, and also the order of reaction. So you have to determine everything experimentally. Now let's say you are asked to calculate the molecularity of reaction. You can go ahead and balance this equation, and as you can see, the equation is actually balanced, right? The equation is balanced. So in that scenario, that shows that the molecularity of this reaction is 1. That is, the molecularity of reaction is 1, because this is the only reactant that we have, and the molecularity of reaction determine heat experimentally. Molecularity of reaction, you can just determine it by balancing the the chemical equation. So if you balance it, you are going to have the molecularity of the reaction. But the order of reaction, we have to determine it experimentally. So the question, we should determine the complete rate law. So now let's go ahead and determine the complete rate law to this question, right? So now what I'm going to do here is that look at this. I don't have to stress myself, so I'm going to follow the pattern of this rate law, because this is the rate law with respect to this reaction. So I'm going to have rates. I can actually pick experiment 1, because I have to pick I have to pick let me simply say any of the experiments in order for me to determine the constant, because the rate constant for this reaction is going to remain the same, right? It's going to remain the same whether they increase the constant of the reactant or they actually decrease it. It cannot affect the rate constant. That's just it. Now the next thing we're going to do is that I'm going to fix in everything here into this rate. Now I can actually follow experiment 1. Then following experiment 1, the rate for experiment 1 is 4.02, right, times 10 to the power minus 5. That is the rate for experiment 1. This will be equals to rate constant is actually K, right? Then multiply concentration of NO2O5, which is the first concentration, which is this. Then I'm going to have it 2.40 multiplied by 10 raised to the power minus K. Right, that's what I'm having. Then all raised to the power of x, which is the order of the reaction. We can actually call this equation 1, right? Then the next one, I will pick experiment 2. If I pick experiment 1 and 2, or I should choose to, I can feel like picking experiment 1 and 3. I'll still have the same answer. So from here, I'm going to have the rate to be what? This is going to give us 1.21 times 10 to the power minus 4. Then this equals to rate constant. Then multiply by, here we're going to have 7.20 times 10 to the power minus 3. And this as well is raised to the power of x. Right? So I'm going to call this equation 2. Now the next thing I need to do is that I have to simplify this reaction. Right? I have to simplify it. So now let's go. Now this is equation 1 and this is equation 2. Now what I'm going to do is that I'm going to, in order for me to get the value of k and x, I'm going to divide I have to divide this. I'm going to divide equation 2 by equation 1, right? That's what I'm going to do. I'll be dividing equation 2 by equation 1. And what you have to note here is that it is very, very, very better you place a bigger value at the numerator, right? A bigger value at the numerator. Why are you? So in this case, I'm going to divide equation 2 by 1, right? So that shows that I'm going to have 1.21 times 10 to the power minus 4, right? Then this is equals to, here I'm going to have 7.20 multiplied by 10 to the power minus 3, all raised to the power of x, right? Then I'm dividing this side as well by 4.02 times 10 to the power minus 5, right? This is also divided by what? Here I'm going to have 2.40 then times 10 to the power minus 3. So now if you look at this very well, this 10 to the power minus 3 will actually cancel each other out. You look at it very well, right? And at the same time, if we are solving this side, that's 1.21 multiplied by 10 raised to the power minus 4 divided by 4.02. Let me get my calculator. So here we're going to have 1.21, right? Then this is multiplied by 10 raised to the power minus 4. Then we're going to have it divided by what? By, this is going to be 4.02 times 10 raised to the power, this is going to give us minus 5, right? So what do you have here? We have this to be actually, everything here is 3, right? Then this is equals to, now 7.20 divided by 2.40, this is approximately 3 as well. So this is going to be 3 raised to the power of x as well. So this we cancel this, right? So in that scenario, we are going to have our x to be equal to what? 1. That shows that the order of reaction with respect to this question is actually what? 1. That is the order of reaction. Now, look at what I'm going to do now. So since I'm having everything here, so the rate law expression is going to be what? We're going to have the rate law expression to be K, then multiply what? Constituent what of NO2O5 raised power what of 1. So the X here is 1, so that's why I'm putting 1 here. Now the next thing is that we have to get the value of what? Of this K, because K is actually the rate constant and it's very, very important for us to calculate it out. So how are we going to go with that? It's very, very simple. We can use any of the experiment actually. Is either we use equation 1 or we use what? Equation 2. So we can use any of them. So now let's just go ahead and solve it. Right, let's go ahead and solve it. Let's go ahead and solve it. So in this case, we're going to have our rates to be, you choose to use equation 1. So you're going to have our rates from here. I can actually make my K sort of formula so that I'm going to have K equals what? I'm going to have R divided by what? Concentration what? Of N2O5, right? So in that scenario, what am I going to have here? So I'm going to have K to be equals to what? The rate, which is the rate of reaction, as far as this one is concerned. If I'm going to use equation 1, I'm going to have it to be, that's going to be 4.02, then multiplied by 10 raised to the power minus 5, right? Then this is going to be divided by what? I'm going to have 2.40 times 10 raised to the power minus 3. Since everything here is raised to the power of 1, I don't need to stretch myself, right? So I don't need to bother myself by actually indicating it. So here, let's simplify further. Let's simplify this further. And let me just simply put the rate here. That is the rate. Let me put it here. So we're going to have the rate equals to what? This is going to be K, then multiply by what? N2O5 raised power what? Of 1. That's the rate. So we have to get our K, which is the rate constant. Now going with this, we're going to have this K to be equals to, look at this. Pressing everything here on calculator, we're going to have this to be 4.02, then multiply by what? 10 raised to the power minus 5. Raised to the power minus 5. Then divided by, we're going to have 2.40 times 10 raised to the power minus 3 times 10 raised to the power, this is going to be 10 raised to the power minus 3. This is what we have. So the answer is actually 1.68 times 10 raised to the power minus 2. That's actually the rate constant. Now, the most important thing that we have to do here is that we have to determine the units for the rate constant. And as far as this concentration is concerned, concentration actually has its own unit in mole per MQ, right? If you represent as this is going to be, let me simply represent as what? As molar. And this is actually rate of reaction, which shows that this particular reaction, this particular reactant is actually changing with time. So you're going to have what? Molar divided by what? Seconds, right? So from here, we have our reaction, which is the reaction rate to be what? To be molar divided by what? Seconds. Then this is going to be, we having it to be divided by what? This concentration of this is actually was molar. So I'm going to have molar here. So I can actually change it. So I'm going to have molar divided by seconds, then simply multiply was 1 over what? Over molar. So in that case, this will cancel this. So I'm having 1 over seconds, which is actually what? Per seconds. So this is actually the SI unit for this what? Rate constant. And in that scenario, we can actually come back here and fix it in here. So we're going to have our reaction rate equals to what? 1.68 times 10 raised to the power what? Minus 2. Then multiply what? N2O5 all raised to the power what? 1. So this is the complete rate law for this reaction. This is the complete rate law that we are asked to calculate for, where this is the rate constant and this is the what? Order of reaction. And at the same time, in this kind of situation, the overall order is going to be what? Is going to be 1. So that shows that this reaction belongs to what? First order reaction. It belongs to first order reaction. So now let's move to the next question.